Hello and welcome. In today's video we're going to take a look at length, volume, area, capacity and mass. So the relevance of this, the reason why as engineers we need to be able to perform these calculations and we need to be able to perform them correctly is to ensure accuracy when marking out and measuring components. So accurate measurements are a fundamental part of engineering. Often we will need to work out certain measurements as well. So you've got a technical drawing, it's not going to give you every piece of information on it, you're going to have to work a few little bits out. So this can be to help us design, mark out and manufacture parts as well as setting up certain assemblies. So if we have a look at this drawing, we are given the overall length, the width, thickness and the distance between the hole centres. So you've got the distance between the hole centres here, overall length down here, you've got the thickness here and you've got the width of the bar here. So we're not given the distance between the centre of this hole here and the end, and we're also not given the distance between there and there, although that, if we're going to work from a datum edge, we work from this end here, we're not going to need this. We're also not given the distance from the edge to this line here, but as you can see on the drawing it's a centre line, which means it's in the middle of this 25 here. We're not given the radius on the end either. So the overall length is 83.5mm, it's 25mm wide. So where is this datum point? Well, if we look at this 25mm wide, that's going to mean if this radius here was a full circle, it would be a 25mm diameter circle. So the radius is going to be half of that, which is 12.5. So that 12.5 there as well is going to give us the distance from this edge here to the centre of that hole, which is also going to be 12.5, because this radius here will be measured from this centre point. So now we've got that, we've got the radius on the end. What is the distance from the last hole to the end of the job? It's going to be 12.5mm. So how do we mark this out? Well, what you'd do is you'd set this as your datum edge, and you'd mark your 12.5mm to your first hole here, where you would scribe using a set of dividers your 12.5mm radius and then your 19mm hole. Then from the edge again, you'd add 12.5 onto your 16.5 and you'd mark this hole. You'd add your 12.5 onto your 29, mark this one, again add it to your 42, add it to your 54, add it to 64, mark all of them. And then what you'd do is you'd measure 83.5 and mark the end off. So that's it for measuring length. So for measuring volume, so according to the Oxford English Dictionary, volume is the amount of space that an object or a substance fills. It's the amount of space that a container has. The volume of a shape or a part is dependent on the shape and size of that shape. It's a bit of a mouthful. So depending a cube, the volume of a cube is easier to work out than the volume of an oddball shape, for example. So depending on the size of the cube and the shape itself will depend how we work out the volume, but we're going to go into that a little bit more as we go along. So engineers are required to know are required to be able to recognise how complex parts can be manufactured from basic shapes. For example, the engine block on the image is machined from a solid billet of aluminium. If the volume of that billet was far bigger than the engine block was ever going to be, you're going to have a lot of waste material. And if it was far smaller, you're not going to be able to manufacture the part from it. So you need it to be just the right amount of size. So you'd use the drawing, let's say, that someone's done, or if it was a CAD design, you could have it on the computer system. You'd be able to work out what sort of volume cube you're going to need, or cuboid, to be able to machine that engine block out of it. So to calculate volume on a simple cube or cuboid, it's a very simple equation for this. It's length times width times the height. So let's say the length is 4 centimeters or 40mm, the width is 20mm, and the height is 15. It's going to look like this. It's going to be 4 times 2 times 1.5. I've done it in centimeters to make it a bit simpler for this equation. So that gives you 12 centimeters cubed. So the way to imagine that is you're going to have 12 little 1 centimeter by 1 centimeter by 1 centimeter cubes that would fit inside this shape here. So to work out volumes of cylinders and other shapes, to calculate the volume of things that are not square, first you need to work out the cross-sectional area. Now this is assuming it is a constant shape and it doesn't vary in diameter as it goes along. So for cylinders, for a cylindrical shape such as a round steel bar, you're going to need to first work out the area of the circle, which is going to be pi r squared. So pi is 3.14. Radius is going to be r is going to be the radius of the circle. So example, steel bar, 30mm diameter. Radius is half the diameter, so it's going to be 15mm. So 30 divided by 2, 15. So the equation we have is going to be pi times 15 squared, which gives us 15 squared. Sorry, is 225. So pi times 225 is 706.86. So the cross-sectional area of the cylindrical bar is 706.86 millimeters. So continue on from this. Now we've got the cross-sectional area, we need to work out the volume. And to do this, we simply multiply that area by the length. So if it's 30mm bar, give it a length of 100mm. Calculation is going to be the area times the length, so 706.86 times 100 gives us 70,686, which is in millimeters cubed. If we work that out to centimeters to make it easier to handle, it's 70.69 centimeters cubed. That's been rounded up. So calculating area, again we've just done this for the diameter of the circle. To calculate the volume of other shapes, you first need to calculate the area. For example, if you're going to use a hexagon, you're going to use this equation here. So we've calculated the area for a circle. The area for a square is obviously its length times height, or length times width, as we did on the cuboid. So this is for an oddball shape. You can get equations off the internet quite easily for many different shapes. I've just done a hexagon here, as a hexagon is quite a common shape in engineering. So the area is equal to 3 to the square root of 3 divided by 2, and then a squared. So that a is the length of one side of the hexagon. Obviously it's going to have 6 sides, all sides are going to be the same length. So if we imagine a hexagonal bar and the sides are 5mm long, so all the 6 sides are going to be the same length. So we put that into this equation here, we get a cross-sectional area of 64.95mm squared. So to find out the volume of the bar, you simply multiply it by its length again, as we did for this cylinder. So we've gone a bit forward there. Yeah, so you'd simply multiply that by its length. So if it was 100mm, you'd times 64.95 by the 100mm. Sorry, next slide. So looking at capacity, to work out the capacity, we look to calculate the internal volume of a hollow container. For example, the cubic capacity, that's easy for me to say, of a cylinder inside of an internal combustion engine. That would be probably one of the main things that that I could think of for engineering wise, working out the CC of your car or your moped when you just bored it out. So, more importantly, volume of coffee I can fit in my mug. So, as you can see by the pictures, I measured a mug. I got my vernier out my toolbox and I measured one of my mugs. So the capacity, to work out the capacity, all you need to know is the internal diameter and the internal depth. So essentially you're working out a cylinder that doesn't exist. It's the volume of a cylinder that isn't there. It's the hollowed out part of the mug to work out how much coffee you can put in it. So the diameter of this was 74mm and the depth is 92mm. Assuming that the coffee cup is perfectly square and doesn't have any radiuses inside it, radiuses and stuff will obviously make a difference, but for this example we're going to assume it's completely square. So first thing that we work out is the area of the circle, which is 74 divided by 2 to give us the radius, which is 37. So pi r squared gives us 4,300.84 millimeters squared. That's the area of the circle at the top. So area times the length, which in this case is the depth of the inside of the mug. And the depth is 92mm, so it's going to be 4,300.84 times 92, which gives us that behemoth of a number there, 395,000 677.2 millimeters cubed. So divide this bit by 1,000 to give us it in centimeters cubed. Gives us 395.68 centimeters cubed. Again, that's rounded up to 2 decimal places. This means that the coffee mug, when filled to the brim, it'd have 395.68 milliliters of Go Faster juice. So it's going to have 395.68 milliliters because it's going to be 395.68 centimeters cubed, or that's its cubic capacity. Okay, so this can of course be done for different shapes. They just need the area and the length. So if this was a hexagonal mug, for example, you could work it out using the way we worked out for the hexagon. If it was square, you could work it out using a square. If it was rectangle cross-section area, you could work it out like you would for a rectangle. So again, you just work out the area of the cross-section, the area of the cross-section, and then multiply it by the length or the depth. So moving on to mass. Mass is defined as the quantity of matter in a body. So if an item is subject to gravity, if the item is subject to gravity or in a zero gravity environment, the mass does not change. So weight is determined by the mass of the object and the gravity it is subjected to. So the weight of something is when it is in a gravitational environment. So how much I weigh here on Earth is going to be a lot more than how much I weigh on the moon. How much I weigh after we come out of quarantine or lockdown is going to be a lot more too, but we're not going to go into that. So how much I weigh on Earth is going to be a lot more than on the moon because the gravity is different, but my mass will stay the same. Okay, so weight and mass are not the same. Try not to get confused between the two. To work out weight from mass, we use this simple equation here, which is weight equals mass times gravity. So weight is measured in newtons. Mass is measured in kilograms. So it's not gravity, it's gravitational acceleration. So weight equals mass times gravitational acceleration. So the weight is measured in newtons, mass in kilograms, and gravitational acceleration is in meters a second squared. So on Earth, the gravitational acceleration is 9.81 meters a second squared. We use this as a constant. Technically, on different parts of the Earth, it will be slightly different because the gravitational pull across the whole planet isn't actually exactly the same. There is a variation in it, but this is sort of an average worked out. So if we have a part that has a mass of 3 kilograms, so example that steel cylindrical bar, let's say it's got a mass of 3 kilograms, we want to work out its weight on Earth. So we multiply the mass by the gravitational acceleration, which is 3 times 9.81, which is going to give us 29.43. So that's the weight in newtons, so it needs to be written as 29.43 newtons. So that's it. That's all you need to do to work out the mass of an item, or the weight of an item from the mass. And again, if you were doing it the other way around, if you had the weight and you need to work out the mass, you just reverse the equation. So it would be, go back. So it would be, instead of weight equals mass times gravity, it would be mass equals weight divided by gravity. And that would give you the mass rather than the weight. And that's it. So list of references where I got all my stuff from, because not all the images are mine, and the book at the bottom there that I've used to get my information from. Thank you very much.